Integrated Services Digital Network, also known as ISDN. The telephone companies built their networks on an analog infrastructure. Once the development of digital communications matured, though, the telcos knew that they had to play in this new market to secure their place in the telecommunications industry. So they came up with ISDN. In this nugget, we're going to start by defining ISDN and the development path. Then we will discuss its protocol makeup. After that, we will develop the ISDN model by talking about and identifying the terminals and the reference points that are involved. We will also break out the channels in an ISDN connection. And then we're going to talk about the two services offered within ISDN, the basic rate and the primary rate. And we're going to include a discussion on the service profile identifier needed for BRI operation in North America. ISDN can be defined as a set of communication protocols that were developed by the telephone company, and the development led to the ability to carry data, voice, and video over the telephone network. Essentially, it was an attempt to digitize the telephone network. That's just simply stated. So let's talk about why we would want to do this. And that discussion has to start with a discussion or a comparison of analog and digital communications. When we're talking about voice, we're talking about analog communications, and that's simply a sine wave. The communication is represented by a change in voltage and a sine wave. Now, when we're talking about digital communication, it's more defined as a discrete step. In other words, we have different values that we change between. If this could be a 1, this could be a 0, and these could be binary values. So when we go up in voltage, it represents a 1, go down in voltage is 0. What's the advantage of that? Digital communications and its discrete steps offer less noise and at the same time faster transmission rates. And that's what enables communication to go beyond just voice and into data and video as well. Now let's take a look at the history that led to the development of the Integrated Services, let me add the S there, Digital Network, also known as ISDN. Okay? As we said in the intro, the telephone company started out with an analog infrastructure, and that is known as the plain old telephone system, POTS for short. And this analog infrastructure extended out to homes. So one home, let's say in Texas, could make a call to another home in New York. In fact, this could traverse the world as well. All analog communications, in other words, the support of voice, but not data or video at this time. Then as the digital communications matured, again, the telephone company knew they had to play in that market, so they developed what was known as the Integrated Digital Network. You can view this as a subsection of the POTS. In other words, in the backbone area of this analog infrastructure, they started to develop digital communication support, known as IDN. Now, the problem is IDN originally wanted to extend all the way out to the homes in the neighborhoods, and that would take the support of fiber being stretched out to those areas. Okay, they couldn't run on the old grade copper that they have in this analog infrastructure. Now that became too expensive, so they decided to go with a different plan, and that plan was having the IDN serve as the backbone infrastructure for the digital network, but they had to extend over their existing analog infrastructure to the home and allow digital communication to take place over those copper lines that extended to the home. And this is where we're going to focus our energies in this nugget in identifying and understanding the components involved in the ISDN network. In other words, the extension of the IDN from the ISDN switch here in that digital backbone all the way out to the home or the place of business, wherever the customer prem equipment was located. Keep in mind that ISDN is a set of communication protocols, not just one protocol. So that set of protocols spans 3 layers of the OSI model, and it's the bottom 3, the physical, the data link, and the network layer. Keep in mind that this is going to operate, though, under the rules of transmission as all other protocols do. In other words, at the network layer, we're going to set up a packet. At the data link layer, we're going to frame that packet and all the upper layer information for transmission over the physical layer, where we're going to transmit this in bits, 1s and 0s, across the physical medium. The protocol set that is involved in ISDN is too numerous for us to define them individually in this nugget. So what we're going to do is we're going to focus on the body that is used to standardize those protocols, and also we're going to highlight a few of those protocols as they define or pertain to the ISDN development. So let's start with the body. It is the International Telecommunications Union, sometimes referred to as the ITU, that is given the responsibility of making the recommendations for these protocols. So let's talk about the ITU for a second. It is truly a global organization. In fact, it was set up by the UN, the United Nations, back in 1947. And its job was to set out communication standards for telecommunications and at the same time allocate frequencies for use within those standards. So we have the development of standards here as one of the primary functions. And some of the standards that were defined are listed below here. Now, because they're responsible for so many standards within the whole realm of telecommunications, not just strictly ISDN, they divide these standards into series. Okay, and these series are identified by an alpha character. And these alpha characters will then have a description associated with them to tell you what these types of standards are going to pertain to. Let's start with the E series. The E series was used as a recommendation for ISDN over the telephone network. So what we're going to do is just say ISDN over the telco, which stands for telephone companies. All right, some of the highlights or standards within that series are E.163, which is going to be the numbering plan for what was known as the PSTN, Packet Switch Telephone Network, again referencing the digital network backbone within the telephone company. And another is E.164. Now this is the International ISDN Addressing Standard. Okay, now if you ever want to look up any of the standards that we're discussing now and are about to discuss, there is a website that you can go to. It's www.itu.int, again for international usage. You won't be able to read the recommendations right off the website. There's a fee, and then they will send you the recommendations, but if you ever need one, this is where you would get that. All right, moving on. Let's look at Series I. Now, I series has to do with ISDN concepts and interfaces as far as different aspects of the protocol development. So concepts and interfaces, and what we're going to find here is I-400. Now, I-400 is labeled as the User Network Interface, or the UNI, if you will. Let's label that prior to moving on, User Network Interface. Now we have I-411, and this is going to pertain directly to our nugget today. This is where we're going to define the ISDN reference points. Now these reference points are very valuable in letting you know or defining the electrical standards for communication between the different devices. These devices are going to be called functional groups, or at the same time they can be called terminals. And this is another section of our nugget that we're going to discuss today. So I-411 discusses the reference points. The next series that we're going to move into is the Q series. This has to do with switching and at the same time signaling. Now this switching and signaling can take place at any of the three bottom layers of the OSI model. Remember that we said these protocols span the physical, the data link, and the network layers. With that in mind, we've got an example here of Q.921, which is ISDN in reference to LAP-D, which is Link Access Protocol over the digital network. This is a layer 2 aspect of our signaling. And then we also have the Q.931, which is the ISDN network layer, or layer 3 communication and signaling. So far in this nugget, we started out by defining the history that led up to the development of ISDN and its purpose. We also looked at the protocols involved in the body that defines those protocols. Now we're going to build the ISDN model. And in order to do that, we're going to need to study the terminals and the reference points. We're going to start off with the terminals. All right, terminals can go by another name, and they can be called functional groups. These functional groups outline physical devices that are involved within the ISDN connectivity. Again, this connectivity extends from what we labeled as the IDN out to the customer prem, which can be a house, an office, a building, whatever it may be. It's this link over the existing analog wiring or copper wiring that we need to establish digital communications over. Notice down here in our diagram, for the sake of our discussion in this portion of the nugget, I swapped the sides. In other words, this representing the customer prem and this being the telco or the telephone network, I've switched that. The telco is now represented from the ISDN switch all throughout the network. So we have the telco here. And in the customer prem equipment from this device over, and we're going to identify each of these devices involved in the customer prem as we go through this nugget. So here's the customer end. All right, let's start with the far left. What we're going to define here is terminal equipment. Now, this is what is known under the Cisco umbrella, and all of the documentation is terminal equipment. But you also will find some documentation out there that refers to this type of devices as terminal endpoints. Keep in mind they're talking about the same type of devices. They're simply interchanging equipment and endpoints, okay? So don't get confused there. All right, there's two types. There's terminal equipment 1, which is type 1, and also terminal equipment type 2. Let's start off with a description of type 2, and we'll hold that right down here. So this is terminal equipment type 2. This means it is a regular piece of terminal equipment. It is not ISDN ready. Keep in mind that analog communication is what was functioning prior to digital communication. So the regular handsets, like the telephone sets or things of that sort, that were out there, only defined analog communication. So these are not ISDN ready. So let's do our little symbol there of not ISDN ready. And because of that, they're going to need a piece of equipment to adapt them into the other devices that support ISDN. And we'll talk about that after we define the TE1 equipment. This is, again, the terminal equipment type 1. And this is ISDN ready. In other words, it has the signaling and the specifications allowing it to talk directly to the ISDN interfaces of other devices, okay? Now, what we need to bridge the gap between the TE2 and the ISDN equipment over here is called a terminal adapter, a TA, and we see it here, a terminal adapter. Simply stated, it takes the old type of equipment and conditions the line signaling so that it can talk into a digital environment. Now, we're here at this point, the digital environment. This is where we term network termination points, okay? So NT, again, they have two types, 1 and 2. NT2 is what we run into first. So directly from our terminal equipment that is ISDN ready or the terminal adapter, we run into terminal NT2, which is a network termination in both of the models. We have NT2 at this layer, okay? So we have connections being made here, and then we have connections running through an ISDN alien into the terminal adapter into the NT2. All right, at that point, we change into what is known as network termination type 1, and we can do that in both models. And this is simply the devices that are programmed and ready to talk into the telco, which is the ISDN switch and the digital network backbone here. So these two devices are assigned the responsibility of getting us ready to talk to the telco network. At this point in the discussion, you might be asking, why have two separate network termination points, type 1 and type 2, in series? In other words, in the same connection. We can see the terminal equipment being a type 1 and 2 because that gives us different models. In fact, one here and one here. But they're not working in series where you would go from a TE2 to a TE1 and then into the network. So the answer is this. The NT2 was originally designed as an interface into what is known as an ISDN PBX. PBX stands for Private Branch Exchange, okay? This is the problem. They're not used that often, and in fact, in many diagrams and in many white papers, things of that sort, you're going to see NT2 left off of this diagram. You're simply going to see a TE1 connected into an NT1 or a TE2 to a terminal adapter into an NT1. Okay? It doesn't mean that they're not out there. It just means that they're very rare, and you may not see them within your career time. If you do, it is important to know where they reside, and we show that here. If not, it would simply skip this step here, or this piece of equipment, and be connected directly into the NT1. Now, the NT1 is identified as the local loop terminator. Why does it have that name? Everything that is here at the customer prem is identified as a local loop, and this is the termination point for that local loop. It's simply a way of letting us know that we are leaving the customer prem equipment and now interfacing into the telco. With that, we've identified the ISDN terminals or functional groups as physical devices that are used to adapt the electrical components of our data for transmit or transmission over a digital network. Now we're going to have to move into what is known as the reference points. These reference points are used to characterize the different interfaces used in ISDN. So down here we see our model. Again, we see the terminal equipment, TE1 and 2, terminal adapter, the network termination 2, network termination 1, and then the telco network represented by the ISDN switch and the network together. Now we're going to talk about these reference points again that characterize the interfaces for ISDN. So these reference points exist in between the devices. These lines as they're drawn will each be a different reference point. The ITU recommendation that outlines the reference points again is we talked about this earlier, dot 411. The four reference points that we're going to discuss today involved in ISDN are the R, the S, the T, and the U. I'm going to give you ways of remembering the different reference points as well by their designated letter. All right, first of all, we're going to start with the R reference point. The R reference point exists between terminal equipment 2 and a terminal adapter. The way to remember this, remember, we were dealing with analog communications, trying to make the adaptation into digital communications. So the regular devices supported analog. So R, reference point for the regular devices being connected to a terminal adapter. We see that here. The next reference point we're going to have is S. Again, if this is regular, the old type analog communications, the digital communication or digital ready devices should be represented by a special identifier. And again, S for special. This is the special reference point. It's between the terminal equipment that supports ISDN and NT2. So it'll exist here as well because the terminal adapter obviously is a piece of terminal equipment that supports ISDN communication. And it's in between, connected to the NT2. The next one we're going to look at is the type of T. Now this is going to be between NT2 and NT1. This is simply a termination point referenced by the T reference point. These termination points between network termination 2 and network termination 1 exist in both models. And the last one we're going to look at is the U reference point. That exists between NT1 and the telco, or the telephone company network back here. There's a bit of a story behind this. In Europe, when you connect into an ISDN model, as we're developing here, the NT1 device is actually supported at the telephone company as well, as we would see here. So the telco extends into NT1 in Europe. And because it does, using an RJ45 connector for connection, 2 of those wires are going to support data, and then 2 of those wires are going to be used for power to the device. Well, this is the problem. In North America, the NT1 resides at the customer prem, as we're used to here, and that power is hard to run, obviously, between the long distances from the telco over to that device at the customer prem. So we simply only have, in North America, the 2 wires being used for data transfer. The power comes from plugging into the wall somewhere. Okay? And because that is true, it is unpowered. And this is where we get our U interface that exists between NT1 and the ISDN network or at the telco. This U obviously identifies the division 2 between customer prem and the telco. Remember that we talked about in our terminals that the NT2 type of terminal is sometimes omitted from the connection. In other words, from TE1 straight into NT1. Because this can happen, or the NT2 and NT1 can be combined, it was mandated that reference point S and reference point T are electrically the same. And it makes sense, right? If you're able to take out NT2 and still have that same connection from a TE1, these must have the same electrical characteristics. Now we've completed our ISDN model. To include terminals or functional groups, here we have the terminal equipment type 1, terminal equipment type 2, the terminal adapter, and then the network termination equipment type 2 and type 1 that are involved in the ISDN model. We also have our reference points that we just discussed. Reference points R, S, T, and U. Next, we're going to look at the channels. Channels can be defined as logical pipes that exist on physical ISDN connections. And here we see an example of that. I have a physical ISDN pipe represented here. Within that pipe, I have logical divisions. And these channels or logical divisions can be defined as B or D channels. And they can exist individually. In other words, this can be a B channel, and this can be a D channel, and each of these channels are going to have different characteristics involved. We'll start our discussion with the B channel, also known as the bearer channel. And the reason it's known as the bearer channel is because it bears the responsibility of carrying the data across this ISDN connection. So Bs are dedicated to data communication. Another way of putting that is they are identified as clear channels, which means that they carry no signaling, just completely dedicated again to the data transmission. Okay? Now the reason that can happen is we have D channels here, and the D channels are responsible for signaling. They require all the overhead to happen within this one single channel for ISDN, which means that B channels come in 64 kilobits per second, and every bit of that 64 kilobits can be dedicated to data. Now the D channel can come in 16 kilobits or 64 kilobit flavors, and that's going to be dependent on which type of service within ISDN we use, either the BRI or the PRI, and we're going to look at that in more detail later. The thing to remember is that regardless of the type of service we use within ISDN, whether it's the primary rate or the basic rate, this D channel is still going to be used for signaling. All right, the combination of the characteristics of the B channel and the D channel give us the advantages of ISDN over the conventional modem communication. The B channels being combined for 64 kilobits apiece is what allows us to have a transfer rate higher than the speed of the modem. So our transmission across this link is much greater than we can have with modem communication. Then the D channel with dedicated signaling is what gives us a faster setup. It also gives us a faster teardown, but the most important thing is the setup time for setting up modem communications are slower versus the ISDN communications because of this dedicated D channel. We started this nugget by defining exactly what ISDN was, and then we looked at the set of protocols that were involved in its delivery. We also built the ISDN model using the terminals and the reference points. And then we just got through talking about the channels involved in ISDN. Now we're going to talk about the types of service. And the type of service we're going to begin with is the basic rate service, or basic rate interface, which we see here. It is also known as 2B plus D. The reason for that is, as we define our ISDN pipe, or the physical connector on ISDN, we talked about logical channels. Well, as you can guess, there are 2 B channels represented there, and 1 D channel that is used for signaling. The next point of discussion is going to be bit rate. If you recall from our channel discussion, the B channels can carry 64 kilobits per second a piece of data across that ISDN physical link. And in the D channel we discussed could be either 16 or 64 kilobits per second. Well, in the basic rate interface type of service, the D channel is going to be 16 kilobits per second. So that gives us a total bit rate at this point of 144 kilobits per second. We also have overhead that is assigned to that too, so you will have a higher bit rate that you're going to receive as a service from your telco or your provider, but this is actually the bit rates assigned per channel on the 2B plus D type of service. Let's step back for a moment to the 30,000-foot view to see exactly what we're accomplishing here. We have our place of business, whether it's your home, your office building, or whatever, and we also have a representation of the telco. Connecting the two, we have an ISDN link, and in that ISDN link, we have logical channels represented here on the BRI by 2 B channels and a D channel. Now, when we make those connections, 2 B channels and a D channel across this link, we have to have in North America what's known as a SPID. Operates as a pseudo password, if you will. It has to match on each end in order for ISDN services to be allowed through that link. When I list the SPID as a requirement, I'm talking about a requirement in North America for basic rate interface type of connections, not for the primary rate connections. Now let's go further in defining what a SPID is. It's a service profile identifier, and it has a function, and we've mentioned that earlier. It serves as a pseudo password. Now it can be defined as a numerical string assigned by the telco to each B channel on an ISDN connection. So let's take this into pieces here. First of all, the numerical string. This string can be represented in many ways, but we do have a generic format that most vendors are following today. And that format has 14 numerical characters. And the way they're divided is this. You have your 10-digit phone number, and then we also have, following that, 2 digits that are termed the sharing terminal ID. So the sharing terminal ID, and then we have 2 other characters that represent the terminal ID specifically. Now these characters here, the sharing terminal ID can range from 1 to 32, and then the TID can range from 1 to 8. All right, so you're going to have your individual phone number, which should be unique in itself, but also at the same time, these other identifiers as well within the format of this numerical string. Now let's look at the second part. It's assigned by the telco. In other words, if this is your customer prem or your place of business, and this represents the telephone company, they are going to tell you what your SPID should be here, and they've already got it assigned in the switch as it exists at the telephone company, and there is a handshake process to make sure that these two match before the ISDN service is allowed. And in the last part, it should be assigned to each B channel on an ISDN connection. So here, logically, we depicted one SPID as being shared. But really what's happening is, on this BRI that's extended from place of business to telco, you're going to have a SPID for each B channel that passes data. Keep in mind that each SPID must match on each end of this connection. So this is going to represent the two B channels. If I have SPID number 1, 1, 2, 3, SPID number 1 is a switch, should also be 1, 2, 3. Obviously a simplified representation of our generic format here with our SPID, but just to get the point across, they must be unique as well. In other words, SPID number 2 can't be 1, 2, 3 as well. This will have to be something different. Generic representation, let's say 1, 2, 4, and then here it's a switch, identify as well. If for some reason these are different, then the ISDN service is not offered across this link. To avoid confusion, let me distinguish again. This generic representation I'm talking about here in 1, 2, 4 is not the same as the generic format that is used by the telcos in representing SPIDs when you're actually going to order this service. All right, the last section of this nugget is going to be a discussion on the primary rate interface. This is the advanced service or the larger bandwidth service of ISDN, larger than the basic rate interface. All right, it is also known in some cases as being 23B plus D. Now this is in North America, and in Europe it's known as 30B plus D. You can tell that these AKAs are simply to simplify how many of the different channels we have associated with each service. All right, so I distinguish between North America and then also Europe or other countries that offer ISDN service. So within North America, we have a T1 type of interface that we can offer, or a bandwidth that we can offer from customer prem over to the telco. And within that T1 service, we are going to have a representation or logical pipes, B channels and D channels within our ISDN physical connection. All right, so really the only change here is how many of these pipes we're going to have. This is going to be pipe number 1, and then this is going to represent pipe number 23. So we have between 1 and 23 B channels, and then we also have 1 D channel with the ISDN connection. So we have a total in North America of 24 channels altogether. 23 of those represented by B channels, 1 by a D channel. Now, the D channel is not going to be 16 kilobits per second as we saw on the basic rate interface. In this case, it's going to be 64 kilobits per second as far as its signaling ability and bandwidth available to it. So we're going to have a total bandwidth that's available here of the 64 kilobits for each B channel here. You know, it says 23 times 64, which would be 1,472. And then we also have this 64 kilobits giving us a total transfer bit rate of 1536. Now, when we fit that into a T1, this is kilobits per second, which operates at 1544 kilobits per second, or more commonly represented as a 1.544 megabit connection, then we can see that we have a little bit of overhead room left there. But this is essentially what we have is 23 plus 1. Now on to our discussion of the primary rate interface outside of North America. The common transmission ordered there is called an E1, which has a maximum throughput of 2.048 megabits per second, or 2,048 kilobits per second. So what it's going to have is more B channels. I mean, you can see it has more room than our common T1. This is how it's going to be divided. The B channels are divided 1 to 15 on the B channels. Then the 16th channel is the D channel, and then B channel 17 all the way up through 31. This is going to still allow for our signaling at 64 kilobits per second on the D channel, and then all B channels still offer the same 64 kilobits per second of the data transfer. It's simply a matter of the D channel being in the middle of all the B channels, where here was the last channel, which was the 24th channel, represented in that ISDN connection, primary rate interface to be more specific. Here we're going to have it at the 16th channel. Other than that, there are no differences in the type of signaling that occurs, and then also the fact that each B channel can carry 64 kilobits per second. In this nugget, we started out by defining what the ISDN protocol was. We also defined the history that led up to its development and the fact that it was designed to carry not only voice but also data and video in a digital format over existing telephone lines. We also looked at the set of protocols that were involved in defining ISDN. The International Telecommunications Union, or the ITU, was also identified as the body for making those recommendations. Then we went into making the ISDN model. We identified the terminals, which were the terminal equipment type 1 and 2, the terminal adapter if needed, and also the network termination type 1 and 2, and the reference points, which were the R reference points for the non-ISDN ready terminal equipment, and then the S, T, and U reference points that serve further on down the line within our model. And in the channels, we saw that there was a B channel supporting 64 kilobits per second of data transfer, and a D channel that took care of the signaling for us in the overhead, and that could either be with the basic rate interface, 16 kilobits per second, or the primary rate interface, it would be 64 kilobits per second. Further defining the basic rate interface, we saw that it was 2 B channels plus 1 D channel. It also required within North America a SPID, or Service Profile ID, which is a unique ID that works as a pseudo password. And then ending up with the primary rate, we saw that it can be in support of a T1 or an E1. The T1 called for 23 B channels and 1 D channel. The E1 had 30 B channels and 1 D channel, with the D channel existing as the 16th channel. I hope this has been informative for you, and I'd like to thank you for viewing.